Assalamualaikum and good day, dear student. So now let's continue inverse interpolation methods for inverse Lagrange interpolation method. Okay, we have done with the first part. So now let's continue our discussion on inverse Lagrange interpolation method. Okay, so before we proceed with inverse Lagrange, let me recall that previously in Lagrange interpolation methods, so again we want to estimate our fx, okay, for the given x. We estimated by using polynomial degree n. Okay, so how we construct our polynomial Lagrange? So this is the general formula. It's given by summation of I equal to 0 until n Lix. Okay, so this is Lagrange term multiply with fsi. So fsi here is the known data point, where Lix is the Lagrange terms is calculated by using this formula is the product of from j equal to 0 until n, but j cannot be equal to your I. Okay, where the product of is actually this fraction here. Alright, x minus xj divide with xi minus sj. So that's why j cannot be equal to I. If j equal to I, then this term become 0. Okay, so for example, if your n order of your polynomial is 2, alright, means that you have 3 data points. So you want to estimate fx is approximated by fp2x. So insert into this Lagrange formula is a summation from I equal to 0 until 2 of your Lagrange term Lix multiply with fsi. So if we open this summation, okay, so summation means the linear combination must be, we add every term, okay, we sum every term here. So starting from I equal to 0, so we have L naught x time with fs naught. Okay, so this is known data from your table, plus L1x time with your fs1 plus L2x time with your fs2. Okay, so I recall back how to get your Lagrange term. Okay, let's say I show you only the first part. So remember how to construct our first Lagrange term, L naught x. Okay, so L naught x, so here I equal to 0. Okay, so means that we must to have a product of j from 0 until 2, but j cannot be equal to I, means that j cannot start with 0. So we need to jump. Okay, so if we open this product of what you have here, okay, so you should have x minus, so j cannot start with 0, so j must start with 1, x minus x1, and then multiply with x minus x2. Okay, and then over, so here is xi. Okay, so here is actually x naught because the formula is actually xi, so I equal to 0. So what we have below here is x naught minus x1 multiply with x naught minus x2. Okay, so it's easy to remember. The notation here must be same, okay, above and below here. So this is how we get our L0. So how to get L1 and L2, so I leave it to you, okay, because we already discussed this before. Okay, so now we move to formulation for inverse Lagrange interpolation. Okay, so now let's start. Now in inverse Lagrange interpolation method, so similar with inverse Newton, this time we want to estimate our x. Okay, so we approximate x by using our polynomial degree n based on the given or the given f value. Okay, we know f, then we want to estimate our x. Alright, so the formula is same, is summation from I equal to 0 until n. But now for your Lagrange term, instead of you plug in x, so now you plug in your f here. Okay, because given f, given the value of function, you want to estimate what is your S. Alright, the other way around, reverse process. And then you will multiply with the known data from your table xi. Okay, so where LIX, again, this is the Lagrange term. Sorry, it's not LIX, should be LIF. Okay, so now this Lagrange term is given by product of j equal to 0 until n, but j cannot be equal to I. Okay, so what we do here is we calculate the product of this rational function or fraction here, which is f minus fj divided with fi minus fj. Okay, so this is how we calculate our Lagrange term. Okay, for example, let's say we want to construct n equal to 2. Okay, polynomial degree 2. So we want to estimate the x, okay, by using polynomial degree 2. So how we construct our Lagrange, inverse Lagrange polynomial is a summation from I equal to 0 until 2, LIF. So f given later, okay, multiply with your SI. Alright, so this is equal to, if I open the summation, is L naught F times with S naught plus L1 F times with S1, and then plus L2 F times with your S2. Okay, so how to construct the first Lagrange term? Okay, so you refer here. So you refer to this standard formulation here. Alright, how to get the Lagrange term. Okay, so if I expand this, what we have here is actually f minus f1 times with f minus f2, and then divide with f naught minus f1 times with f naught minus f2. Alright, and then we multiply with x naught, and then plus for the second Lagrange term is f minus f naught times with f minus f1, f2, means in the above part we cannot minus with ourselves, maksudnya means that if I equal to 1, so we cannot minus with f1. So below here is f1 minus f0 times with f1 minus f2, and then you time with your x1. Alright, and then plus the last one is f minus f0 times with f minus f1 over f2 minus f0 times with f2 minus f1, and then multiply with s2. So this is how we construct the inverse Lagrange interpolation. Okay, so next we will discuss on example. Okay, so now we focus on the same example. In a chemical reaction, the concentration level of a product at time t was measured every half an hour. The result of the experiment are tabulated in the table below. So again, this table is about time t and also concentration. So the function is actually the concentration at every t. Okay, so this is CT, means that for every time in hour we can estimate, or we can have the data value about our concentration in the experiment process. Okay, so now you're asked to calculate what is the time taken. Okay, estimate your T when the concentration level of the product reach 0.60. Okay, so again, based on this table, we don't have the value of 0.60, but we have the value for concentration 0, 0.23, 0.5, and 0.67. So we want to estimate somewhere here, okay, when C is 0.6. So we want to know what is the time at that concentration. Okay, so you're asked to perform your estimation by using, so now let's focus on the second part, inverse Lagrange interpolation method. Okay, so again, so this is my data for Ti. So I have here T0, T1, T2, T3, and then I define here as my Ci for concentration. So I have data for C0, C1, C2, and C3 here. Okay, so as I told you, you have the value for your concentration. Okay, now you want to estimate your time. Means that Ct is your function, T is your x. Okay, you must be clear about this. Okay, if you are not clear, then maybe you will do wrong. Okay, your calculation will have a mistake. Alright, so now let's focus on inverse Lagrange interpolation methods. Alright, student. So what we want to calculate, okay, we want to estimate T. What is our T if given Ct is equal to 0.6? Okay, so we want to estimate using inverse Lagrange. Okay, so recall back the formula that I discussed previously. Okay, so now you have 4 data points. Okay, since the question do not mention order of your polynomial, means that you must to interpolate all the data points. Okay, since we have 1, 2, 3, 4 data, so n plus 1 data point means that you want to construct n degree polynomial. So polynomial degree 3. Alright, so we will estimate T by using P3 of our given function value. So here C, concentration. Okay, so means that we want to approximate it by using P3 when C is 0.6. So I straight away plug in the value of our concentration. Okay, so based on the formula, this is a summation I equal to 0 until 3. So we must to have our Lagrange term LIF. So F here is your C 0.60, and then you will multiply with your TI. Okay, because our variable X here is T, is about time. Okay, so if I expand this, I should have the Lagrange term L0 when F is 0.6, and then multiply with T0. Okay, T0 is from our table, is a data point, and then plus L1 0.6 times with T1, alright, our second data point, and then plus L2 0.6 times with T2, and then plus L3 0.6 times with T3. Okay, so now if I expand this, alright, if I expand this, get our Lagrange term. So the first part here, okay, L0 0.6, so you refer back to the formula. Okay, so remember LIC is equal to product of J equal to 0 until n, but J cannot be equal to I. So here is C minus Ci over C minus Cj over Ci minus Cj. Alright. So what I have here is L0 0.6, I must have here 0.6 minus C1, okay, and then 0.6 minus C2, and then 0.6 minus C3, and then divide with here my C0, so 0 minus C1 time with 0 minus C2, and then 0 minus C3. Okay, and then I must multiply here with my T naught. Alright, so my T naught, okay, never mind, I will plug in later. Okay, time with my T naught. Alright, and then for the second one, L1, so I put plus here. Okay, so I write down below here is a 0.6 minus C naught time with 0.6 minus C2 time with 0.6 minus C3, and then I divide with C1. Okay, so my C1 is 0.23, so 0.23 minus C naught, and then 0.23 minus C2, and then 0.23 minus C3, and then I should multiply with T1 and then plus. Okay, so now I want to get my L2. Alright, so I put below here is a 0.6 minus C naught time with 0.6 minus C1 time with 0.6 minus C3. Okay, so I divide with, so my C2 0.5, so below here 0.5 minus C naught time with 0.5 minus C1 time with 0.5 minus C3. Alright, and then I multiply this with my T2 and then plus, so the last one here, okay, L3. Okay, so what I have here, my C3 is 0.67. Alright, so the above one I have 0.6 minus C naught time with 0.6 minus C1 time with 0.6 minus C2. Alright, and then I divide here with my C3, 0.67 minus C naught, and then 0.67 minus C1, and then 0.67 minus C2, and then I should multiply here with T3. Okay, so if you look back here, if I plug in into the value here, okay, means that I insert my C1, I insert my C2, I insert my C3. Okay, and then I insert here C1, C2, C3 here. Okay, because this is all our known value here. Okay, let's say I replace here C1, alright, 0.23, and then here 0.5, and then here 0.67. Okay, similar to here 0.23, 0.5, and 0.67. Okay, and then I plug in here my T naught, so my T naught is 0, so if I multiply here I get 0. Alright, okay, so similar to here, if I substitute the value here, C naught 0, okay, and then C2 0.5, and then C3 0.67. okay, so here 0, 0.5, 0.67, and then I plug in my T1 0.5. okay, you can write in proper way, or you can start from the early stage, you already plug in the value, should be okay. Alright, because all that value is our known data point. And then again I substitute here 0, and then I substitute here 0.23, and then I substitute here 0.67. okay, 0, 0.23, 0.67, and then I substitute my T2 1.5, and then the last one I substitute all the value here, the known data point here. And then T3 is 2. So if you simplify this, okay, means that if you expand all the constant and multiply with your ti. So what I have here is 0.0336 times with 0. No need to calculate the first term, as the first term should be okay because understood. Multiply with 0, you will get 0. Okay, and then plus the second term, my second Lagrange term, I should get 0.1537 times with my t1, 0.5, and then plus my third Lagrange term is 0.6771 times with t2, 1.5, and then the last one is 0.4430 times with t3, 2. So if you calculate here, you should get 1.8248 hour. Okay, so the result is similar with our inverse Newton interpolation. So it means that by using inverse Lagrange, okay, for concentration 0.6, we obtain our estimated time 0.6. The concentration 0.6 can be reached at t is about 1.8248 hour, okay, or 1.82 hour. All right, so again, as I told you, it's somewhere here. All right, because 0.6 is somewhere here between these two data points. So since concentration increase, the time also increase, so the estimated should be in between 1.5 and 2 here, and then we obtain the reasonable result, okay, 1.8248 hour. All right, student, so I stop here. So I hope that you have the idea on both inverse interpolation methods. Good luck, and please do a lot of revision. Thank you.